A team based at Princeton University has accurately simulated the initial steps of ice formation by applying artificial intelligence (AI) to solving equations that govern the quantum behavior of individual atoms and molecules. The resulting simulation describes how water molecules transition into solid ice with quantum accuracy. This level of accuracy, once thought unreachable due to the amount of computing power it would require, became possible when the researchers incorporated deep neural networks, a form of artificial intelligence, into their methods. The study was published in the journal Proceedings of the National Academy of Sciences. The ability to model the initial steps in freezing water, a process called ice nucleation, could improve accuracy of weather and climate modeling as well as other processing like flash freezing food. The new approach enables the researchers to track the activity of hundreds of thousands of atoms over time periods that are thousands of times longer, albeit still just fractions of a second than earlier studies. The researchers were working on it for more than 35 years. They invented the approach to using underlying quantum mechanical laws to predict the physical movements of atoms and molecules. Quantum mechanical laws dictate how atoms bind to each other to form molecules and how molecules join with each other to form everyday objects. The researchers published their approach in a groundbreaking paper in 1985. But quantum mechanical calculations are complex and take tremendous amounts of computing power. In the 1980s, computers could simulate just 100 atoms over spans of few trillionths of a second. Subsequent advances in computing and the advent of modern supercomputers boosted the number of atoms and the time span of the simulation. But the result fell far short of the number of atoms needed to observe complex processes such as ice nucleation. AI provided an attractive potential solution. Researchers trained a neural network named for its similarities to the workings of the human brain to recognize a comparatively small number of selected quantum calculations. Once trained, the neural network can calculate the forces between atoms that it has never seen before with quantum mechanical accuracy. This machine learning approach is already in use in everyday applications such as voice recognition and self-driving automobiles. In the case of AI applied to molecular modeling, a major contribution came in the year 2018 when the researchers found a way to apply deep neural networks to modeling quantum mechanical interatomic forces. In the current paper, the researchers applied these techniques to the challenge of simulating ice nucleation. Using deep potential molecular dynamics, they were able to run simulations of up to 300,000 atoms using significantly less computing power for much longer time spans than were previously possible. They carried out the simulations on Summit, one of the world's fastest supercomputers located at Oak Ridge National Laboratory. This work provides one of the best studies of ice nucleation. Ice nucleation is one of the major unknown quantities in weather prediction models. Currently, climate models obtain estimates of how fast ice nucleates primarily from observations made in laboratory experiments. But these correlations are descriptive, not predictive, and are valid over a limited range of experimental conditions. In contrast, molecular simulations of the type done in this study can produce simulations that are predictive of future situations and can estimate ice formation under extreme conditions of temperature and pressure such as on other planets. Water molecules consist of two hydrogen atoms and an oxygen atom. The electrons around each atom determine how atoms can bond with each other to form molecules. The atoms can exist in literally millions of different arrangements. The magic is that because of some physical principles, the machine is able to extrapolate what happens in a relatively small number of configurations of a small collection of atoms to the countless arrangements of a much bigger system. Although AI approaches have been available for some years, researchers have been cautious about applying them to calculations of physical systems. When machine learning algorithms started to become popular, a big part of the scientific community was skeptical because these algorithms are a black box. In the last couple of years, however, there has been a significant change in this attitude, not only because the algorithms work, but also because researchers are using their knowledge of physics to inform the machine learning models.